Okay, so according to my stream program, I'm live, but since this is streaming over the IOTA account, I don't see any green lights flashing up or anything, so I would need some feedback to know if you guys hear me. Oh, now I heard myself, the stream just started. Okay, welcome back. Yesterday we got interrupted coding because my daughter woke up, and today I also had to postpone the start of the session a little bit because she didn't want to fall asleep. But now everything is fine. She's sleeping, and I guess we can continue. I just need to check back what we did yesterday as the last thing. Did we finish the request, or are there any things missing? We don't have any error messages. We have the timed executor, we have the behavior setup function, we have a function to start requesting a message, and it executes that until we call the stop request function. So I think it looks like the requester is actually done. So I guess we can maybe close this and see what is the next component that we need. So we need 1, 2, 3, 4. I think we need to code 4 more files, and then it should essentially be working. And I guess we also need to write some things in the main.go so we can dump the status of the network and things like that. But I think like 2-3 hours should maybe be enough to finish everything. So let's continue with the booker. So the booker is... I need to get back into the flow. Yesterday in the evening, I was really... everything was really fast. I was really focused. I need to get back into that state. So we put the region here because we're gonna have some booker events again, just to separate it visually. And the booker, just to recap, what we talked about yesterday, is the component that takes care of inheriting the perception from the referenced parents. So we have the booker events. Yeah, I was actually quite tired. I also overslept today and brought her to kindergarten a little bit too late, so I guess it was good to end a little bit earlier. Usually she always wakes me up at like 7 o'clock. She's like, "Papa, wake up," and I'm like, "No, I want to sleep a little longer." But even she slept long today. Booker events struct. So this is empty. And in the booker we have what do we have? We have the events, which are the booker events that we just created. We for sure have a Tangle. We need to have a constructor for the booker. He receives the Tangle as a parameter, and it returns a book object, and then, oops, what did it do? And now we have the events, and the events are book events, and the event that we have in there, we have nothing defined yet. I guess we just call it message booked. I think that's how we call it in Shimmer as well. And then message booked. Oh, it auto-completed that again. So then we store the Tangle, and that should be the constructor for the booker. Then we have our setup function again. I mean, the structure is always going to be the same, so that's really nice and easy, and you don't really need to think a lot about how you do these things. So we get the solidifier, and as a message is solid, then we want to book it, and we will call the book function book, I guess. So we need a book function. And the book function now has to inherit the data from the parents. So I guess the first thing that we need to have are the message objects, which we can retrieve from the storage. Oh yeah, we need to have a message ID as a parameter. And then we will have the message metadata, where we store all the locally derived information of the message. And then we store in the message metadata the inherited color equals, and then I guess we can put that into a utility function. I think I might not have a setter method for this. But for the rest we have a setter method. Okay, so maybe I will just add one here in the model, so I can also set that value. Set inherited color modified bool, and then we can just change this color, inherited color, inherited color, color modified true, and then a getter method that will allow us to retrieve the value that we have stored in there. And then I will just return. So that is it. And set inherited color. Oh no, wait. That is our utility function, so then we need to do this here. Set inherited color. Like this. And then after we have inherited the color, we just trigger our event. Message booked, trigger, message ID. So that should be essentially the core logic. Now we go to the inheriting the color thingy. And it's also not really that complicated. Actually, all the consensus related stuff is really simple, nice. It's not very complex. So we will now need to retrieve the colors from different sources. So we essentially have the color of the payload. So in our case, the payload is color. And then we need to retrieve the color from multiple sources. We need to retrieve the colors of the strong parents of the message. We need to retrieve the colors of the weak parents of strong parents. Weak parents of the message. And then we need to combine that with the color of the payload. So before I continue writing any additional logic here, maybe implement the little utility functions that give us the colors of the strong parents first. So the strong parents will inherit the color of the message that they reference, and the weak parents will inherit the color of the payload in the message that they reference. So I don't know if you guys remember the things that I explained yesterday, but that's how we allow transactions or the payloads to be approved even if they are embedded in a message that is attaching to the wrong part of the tangle. So here we need to have a message again, and then the strong parents, we just iterate through them. Strong parent and the range of the message. strong parents. Then if the strong parent is the genesis, so it's a genesis transaction, then we don't need to inherit anything from there because that doesn't represent any kind of perception. The genesis is shared by everybody, because it's part of the snapshot that you're loading. Then the colors of the strong parents, we need to actually have a return value here. So colors of strong parents equals append colors of strong parents, and then we need to retrieve the color from the message metadata of the strong parent, and then the inherited color. So for the strong parents, we take the color of the message, which is stored in the message metadata. And then for the weak parents, the logic should essentially be very similar. So I can just copy this, but instead of using the message metadata, what we use is we use the payload of the referenced message. And here, instead of strong parent, we write weak parent. And here we write weak parents. And that is how we inherit this. So it's really not that complicated. It's just you iterate over the parents and collect all the values. And then now that we have these information, we need to aggregate them. So we need to iterate over them and kind of check if they are conflicting, and then change the inherited color accordingly. So how do we do this best? Maybe I just append them to each other. So we make an empty list of colors, and then we append our colors of the strong parents. And then we can also append concatenating slices or lists of elements in Go is a little bit ugly. Like, you need to have a lot of code. Other languages usually have some syntactical sugar to make this a little bit easier to read. In that case, it's a bit ugly. I don't really like it, but I mean, that's just the way it is, right? So, and then we need to iterate over this color to inherit. And then we need to so if we have an undefined color, then in the transaction there was no color set, so it doesn't represent any perception, so we can just continue. And then if the inherited color is not equals the undefined color, so if we have already inherited color and the inherited color is not equals the color to inherit, so if we try to combine a different color, so if we would have a message that either in the strong or in the weak parents references two different colors, then you would essentially have a message that combines conflicting perceptions of the ledger state. And in theory, this shouldn't happen because we don't produce these kind of messages here. Like, all of our nodes that we're testing initially are honest. Or maybe we can just introduce a message invalid event, and then we trigger that. Then we don't need to panic. I was just thinking about panicking here, but maybe it's nicer also if we want to test attacks later on, that we can actually deal with this instead of the network crashing. So if we have two colors being combined that are being different perceptions of the ledger state, then we just trigger the invalid message event, message invalid trigger, and then that would be the message.id. And then, or maybe we trigger this out here and we return an error. Because then we don't want to inherit the color. I think that is maybe a little bit cleaner code. So if error is not equals nil, then we trigger the invalid message event, message ID, and otherwise we store it and we trigger the message booked event, and then we need to introduce an error return value here, and then we do message with message ID blah blah blah, try to combine conflicting perceptions of the ledger state. And then we need to give the parameter, so this would be message.id and see errors, error factor. This is already the go-to base errors, which are wrapping the error, so you will see a stack trace. As I don't know if anybody is coding Go, so if you use X errors, error F, then you can use this new wrapping functionality and you will receive a stack trace as the errors will be dumped. So if we have an error, then we will trigger this, and here we need to return. So it doesn't do anything. And otherwise, if everything is fine, we say the inherited color is the color to inherit. So we just iterate through them and aggregate that. Usually all of this is done in this ledger state. So it's kind of a little bit of a simplification, but even in the ledger state, it kind of works the same. It checks out the branches of all the referenced messages and payloads. It tries to combine them, and if there is more than one, then it creates an aggregated branch. And if they are conflicting, then it declares the message to be invalid, and it doesn't even get booked. So that means also you see invalid messages and stuff like that instantly on arrival, and you don't need to walk through the ledger state. Okay, so this is it. I think that was it for the booker. Let's see if there's any booker related things missing. We have the message booked event. Oh yeah, we don't initialize the message event. So there we also need to do message ID event caller. So now this should be fine, I think. We have the tangle, we have the setup, we have the book function, we have the function to inherit the color. If we face two different colors that are different from the undefined color, then we panic. Oh no, we panic, we return an error, and otherwise we just inherit the colors of the referenced children. So that is fine, I guess. So then, what is the next struct that we need? The opinion manager. And then we have the tip manager, and we have the message factory. But maybe let's do the message factory first, because that one is really small, and then we get rid of this little red line here, because I think this is the only error that is left here. And then we can go to the opinion manager, and that's actually going to do the actual consensus. So after the message factory, it's going to get a little bit more interesting. But it's not really... it's pretty simple. As soon as a message arrives, you just add the weight of the issuer to a map, and then you just follow whatever is going to be the heaviest. So it's not really that exciting. So type message factory struct. Maybe we do our funny regions here again. Message factory. Maybe I should read the comments first, if there's like anybody writing things. I have no idea what Scrum is. that like a term? I don't know. We just hang out and voice all the time and organize. And I mean, we have like two weekly meetings on Monday and on Thursday. And whenever something needs to be sorted out, we schedule meetings in between. So we kind of talk every day a few times. And region. Today is, by the way, a really important day because we have finally finished the refactor of the whole data structure, like the parallel reality-based ledger state, and we are currently working on adjusting the unit tests and the integration tests and stuff to see if everything works. And so far, it looks pretty good. So the message factory, it doesn't really have any events. I guess it just returns the message that we create, so maybe I don't even need this. So maybe that's a bit stupid. So then we have, oh yeah, okay, so this whole agile developing method stuff. No, we don't really use that internally because it's a lot of research also, especially for Codesite. I know that the engineering department uses these concepts, and when I was working on IRI before, we also did that. But in Go Shimmer, there's a lot of things where you sometimes need to research, you need to write papers, you need to discuss. So it's kind of it's really like you don't have such a predefined day plan and you know exactly what needs to be done. Sometimes you run into a problem, then you need to have a meeting and you need to discuss it, inspect some things, and so it's a little bit of an unusual work environment for somebody who's used to be a developer. But it's fun. I mean, it's challenging and it doesn't get boring, you know. So then we store the tangle here, we create the message factory, and the message factory essentially has only a single function, which is create message. And in the Go Shimmer code, it is actually doing a little bit more, because it also does the proof of work and it monitors things like rate control and how much proof of work it should invest and stuff like that. But here in our case, we don't have proof of work because it doesn't really matter for the consensus. So we're just gonna create a really simple function to create messages. So we will have to have strong parents. Oh, okay, then we need to have access to the tip manager also. So the weak parents. And then we have the sequence number, which will be an ever-increasing number. Because the way nodes can change their opinion, or you get informed about the change of his opinion, is if a node likes a different branch, or likes a branch with a higher sequence number, then you remove his approval from like his previous approval and you switch his opinion, kind of. So that means even if you have approved something different before, you can always change your opinion to follow the pack. So we have the peer ID, I guess. I think that should be it. Do we have more fields in the message? Oh yeah, we have the payload, of course. I totally forgot about that. So the payload is the color in our case. And these strong parents and the weak parents we need to retrieve from the tip manager, and that should be available here. And that should just have a tips method, I guess. So we can leave it like that for now. Yeah, I really think we will finish. I mean, we needed 4 files to finish, and now we have already completed 2 of them. So the only 2 things that are missing is the opinion manager and the tip manager. Do you guys still hear me? Because somebody wrote I'm gone. Okay. Okay, so the message factory can stay as it is, I guess. So the next thing that we need to have is the opinion manager. Opinion manager. And then we start with our regions again. So type opinion manager struct, and that also has some events again, opinion manager events, and then it has a tangle, and then we can opinion manager events, make a region for that. And then what else do we need in the opinion manager? I guess we definitely need to have our own opinion, which color we like. Which would be a color. Maybe let's add the private properties down here. We need to know the opinions of other nodes, so we can adjust the weight accordingly. So maybe it would make sense to actually have a wrapper around the opinion, so we can also store their last sequence number that we've seen. So maybe call it other opinions, or node opinions or something, or peer opinions. Maybe that's better. Peer opinions, and that is maybe a map between the peer ID and their opinion. And then we need to have the approval weights, and that would be a map between the color and a uint64 value. And then we will have the opinion manager events, and then we will have the opinion. Oops. What did I do? Opinion. And then the opinion is also a struct. And then we will most probably have a color there. And a sequence number. Was it uint64? Yes. Okay. And then we maybe also want to have the peer ID in case we need to access it. And I guess that is okay for the opinion already. We don't really need to know more than that. The opinion manager events, what do we need? We need opinion formed, which gets triggered after the message has been analyzed and we have updated our opinion on this message, or the particular opinion is available for this message. And then we want to maybe also have an opinion changed event where we want to trigger as soon as its node changes its opinion regarding the favored color. So this is then not related to, so this is related to a message, and this is related to our own opinion that we have, and which color we believe is the correct one. So now we need to opinion change the event handler. And now we have the funny interface stuff here again, because Go doesn't have generics. And then we say handler, it's a function with maybe 2 colors as parameters. And then we call that function with params. The first param being typecasted to color, and the second parameter also being typecasted to a color. Okay, and then we can create a new opinions function. Yes. New opinion manager, I mean. So the tangle is passed in here. So this is going to be essentially the whole consensus code. Right, so this opinion manager will have all the consensus related stuff. So opinion manager. Oh. And I mean, so far we haven't written any consensus related stuff, only models. The code shouldn't be so much in the end. Okay. I was just drinking something. So now we have the opinion manager event. And then what were the ones we had here? Opinion formed. That's for a message. And then we have opinion changed. And there we had the opinion changed event handler. And then we have the tangle. And then we have the peer opinions. And there we just need to make the map, because initially we don't know anything about the opinion of our neighbors or peers. Opinion. And then we say approval weights. And there again, we just need to make an empty map that we can write to color view in 64. So that should essentially be the opinion manager's initialization thingy. And now we again need to have the same setup function as we have everywhere else. Opinion manager setup, where the opinion manager subscribes to the events of the other methods, and the opinion manager will be called as soon as the message is booked. So as soon as we know its color, and then we can analyze and add the weight of the message to the color. And then how would we call the function for the opinion? Manage opinion? Opinion manager dot manage opinion sounds a bit weird. Maybe form opinion? Go is, there is TinyGo, so you can compile it down to embedded devices. That's really nice, but I'm not sure if that's already very advanced. I've never really tried that, but in theory it should be possible. And I think they were even funded by Google. Like at first it was a community project, and now I think Google funded them, and so it's a legit project, and they will most probably make a lot of progress soon. Okay, so that was the message ID event, so this should be it. And I guess the first thing that we need is the message object again. And the message metadata. And then we need to check. Okay, how do we do it? That's the first guard. Okay, if the message metadata has an inherited color that is undefined, is an undefined color, then the message didn't make a statement about any of the conflicts. So then we can essentially return. But we need to trigger the opinion formed event, right? I guess we will always need to trigger that. So maybe we can do a defer for that. Events, opinion formed, trigger, message ID. Because there's no reason why we would return an error or not cause this. Okay, so then we need to check if there is already an existing opinion of the peer that issued the message. So we need to check. Why did I write I? And then the message dot issuer. So we will check if we already have an opinion of this guy. If it doesn't exist, then we will initialize the last opinion and store it. So if it's the first time that we hear a statement by this node, then we will say peer is message.issuer. Ready. And then we store peer opinions message.issuer equals last opinion. So we kind of store this. And then we also need to write the sequence number. Right. That's then the message.sequence number. And then we also need to store the color, which is the message dot, or the message metadata dot color. The inherited color, yeah. So we need to store all of this information. Oh, this is a function. And if it does exist already, okay, I will most probably need to return here something, I guess. I will see. So then if the message dot the sequence number is smaller equals the last opinion sequence number. So if we have already an opinion, now we do. If the sequence number that we're seeing is smaller, then we've seen an older message. So we don't want to update anything because we already have the latest opinion of this guy. So in that case, we just return. And then if he didn't change his opinion, so if the color is still the same, then we can also return. Then we don't need to update any weights or anything. And then we need to add the approval weight. Oh wait, but here we need to remove the approval weight. No, only if it exists. Okay, so if it exists and he changed his opinion and we have a later message and it's not the same number anymore, then we need to remove from the approval weights of the last opinion dot color. So the opinion that he had before, we need to remove the weight of this guy. And from the message issuer. So that means if a node changes his opinion, then we first remove his weight from the old opinion, and then we add his weight to the new opinion. And then we add his weight. Oh, and this is a function again. And then we need to, of course, also store the new color in the last opinion. So we need to update the sequence number, and we also need to update the color. So essentially we can, I guess we can do that here even. Sequence number equals message.sequence number, because it's a pointer to the opinion and it doesn't really change. Like we never serialize it or anything. So we can just change the object that we have here and it's stored in the sequence. So then we update this here and then we can do the same with the color. And we only update the things if they pass these guards. But then the question is, maybe we can, because here we need to also add the weight, right? Maybe we can make this be the same flow. The sequence number gets set here anyway. And the sequence number, if we don't set it, 0, so the message sequence number should never be smaller, because we start in the message factory with a sequence number of 1. So that means we can just do it like this. We don't return. And then if it doesn't exist, it creates the last opinion. We check if the sequence number is smaller equals. It is not, so it sets the sequence number. Then we check if the color is the same as we have defined here, which would be undefined because we haven't set it. So that would also pass. Then it would store the color. And then it would remove the weight from the issuer, from the old color. No, that is wrong, and I think that is also the wrong order. No, we only need to do that if it exists, because here we have exists, so we only need to remove the weight if this was a statement that existed already, and then if we update the color here, then we also need to do this first. Because otherwise we have overwritten the last color already. So I think that should be fine. So that would now track the approval weights, but now we need to also check if the approval weight of a particular color has gotten bigger or smaller than the other one. So we will need to have a weights updated function or something, which just iterates over the colors and sets our opinion to always follow the heaviest one. And we maybe also want to have some other additional functions. So opinion manager weights updated, and that thing should just iterate over all the approval weights. Oops. And it should look for the highest weight that we have found. So I guess we need to have a UN64 here where we can store the highest one that we found. And then maybe we also need to have a max color. So as soon as so if approval weight is bigger than max approval weight, or the approval weight equals max approval weight, but the color is smaller than the max color. So essentially, the node will always follow the branch with the highest approval weight, or if they are the same, then it will follow the branch with the lower hash, kind of. So in that case, we would say the lower color. So it is a deterministic decision-making process. So all nodes that see the same transactions will always come to the exact same decision. And then we will say max approval weight equals approval weight. And then we will say max color equals color. And then we track this. And now we need to trigger the opinion when we changed something. So if the old opinion is o.own opinion and the max color that we have is different than the old opinion. Oops. old opinion. So we assign a variable to the old opinion, and if the max color that we found is not the same, then we update our own opinion and we trigger the opinion changed event with the old opinion and then the new opinion. Oh, max color. Maybe we should call it max opinion. That's okay, that is bullshit. Let's approve it. Wait. Okay, and that should be the whole consensus. So the opinion manager should essentially be done. Okay, wait, there's like some questions. And with the branch, where do you... yeah, okay, I would just like explain the weak parents and the strong parents again. So in the Tangle, the way it works today, we only have strong, like you can only approve everything that happened in the past of a transaction, or like in the past of a message, since we have the separation between message and transaction. And if there is a conflict, then everything that attaches to this conflict can not be approved by, like, let's say you attach a message that approves a conflicting transaction that doesn't win the voting process. Then nobody could ever approve you, because approval always means everything that happened in the past. And if they wanted to approve you, then they would also approve the conflict that you are referencing. And the weak approver now allows messages to approve you, but just you. So if you are issuing a transaction that is honest, that doesn't double spend anything, and that spends funds that are completely legit, then somebody else can reference you with a weak reference, but only your message will be, like the approval will only inherit to your message, but not to the stuff that you reference. So that means that you can approve individual transactions that are attaching to the wrong point in the Tangle, kind of. And that allows us to get rid of the reattachments and stuff like that. I don't know if that's clear. If you have any questions, we can also discuss this in the Tangle math, maybe. Okay, so let's think, do we maybe need some more functions? This is the consensus mechanism. Maybe we want to have a getter method for our opinion, so we can retrieve our opinion from the outside, because it's a private property, and maybe the tips manager needs that. O.own opinion. But I think that should essentially be it. So the opinion manager is done. So now the only thing that we need to do is the tip manager, and then I think we're done. So the Tangle, the message factory, yes, okay. So that means I need to create a new file, tip manager.go, region tip manager. And you know, that's also the reason why I like this on Tangle voting, or this multiverse approach, because it's just extremely simple. You don't have any random number generators, you don't have committees or nodes that need to run anything. Everybody will always come to the same conclusion if they have the same perception of mana and the same perception of the Tangle. There's no way for them to ever fall out of sync. And yeah, I mean, you don't have to send around messages. You don't have to worry about any of those things. And even if you lose your internet connection and you don't see the current Tangle, or you're eclipsed or whatever, as soon as the internet connection comes back, you immediately have consensus again. You don't need to have any kind of protection mechanism that protects against these kind of things. So type tip manager struct. It's just simple and elegant. Okay, so the tip manager is most probably going to be a little bit more complex, I guess. Or I haven't really thought about how we could do that, because it's significantly different from the way we are going to implement it in the in Go Shimmer. Because in Go Shimmer we only track one set of strong tips and weak tips, because changing your opinion doesn't happen so often. But I think in our tip manager here, because we are more likely to switch our opinion every now and then, it maybe makes sense to track multiple tip sets for the multiple different perceptions at the same time, as well as we do with the ledger state. So we will just have different sets of tips that we can just switch back and forth, and then by requesting the tip set that belongs to our opinion, we can instantly switch between the different perceptions. So I guess we will have a tip set structure. I will just try if it works like that. I guess it should be possible. But maybe there's also like a more efficient way of doing this. It doesn't, that requires less RAM or something. I don't know. So then we have the tip set. That's fine. So we have a tip manager. We have a new tip manager, which again gets a tangle with a tangle. And it returns a tip manager. And then we do tip manager, tangle, tangle. And the tip manager, I think we don't even need events there. The tip manager is essentially the last component that you will go to. And I cannot really, or maybe for some metrics or analysis or something, but I don't think we need to do that right now. So we don't need to have an event when a new tip is added or something. Maybe we can add it later if we needed to dump some log messages or something. So this is the last file. So we have the tip sets, then we will most probably also have a setup function, the tip manager setup, and then we subscribe to the opinion manager, events, opinion formed, attach events, new closure. And then we, how could we call it, analyze message maybe. So it analyzes the message and determines what kind of tip we are seeing here. And then we need to have the analyze message function. Message ID, message ID, sorry. So since there's a discussion around how many tips you have, and I think at the most sense it would most probably make to have just as few tips as possible in situations where you don't need more tips. So that means that I think by default we will have something like 2. And if the amount of tips is increasing over a given time span, then we will just increase the amount of tips that you reference to reduce the amount of tips again. So if somebody is doing like a blow ball attack or some other kind of attack, then you can fight this and increase your tips, and this essentially makes the attack 8 times less efficient, which should be enough to secure the network. And yeah, if the attack is over, it will just be decreased again. Maybe, I don't know if I can make it into voice, because my girlfriend is currently not... Oh yeah, I guess I could, because she's coming back on Sunday. So after my daughter is sleeping, I guess I can check by. So, okay, so the first thing that we do is, as always, we first retrieve our funny message here from the storage. Oops. Because we need to analyze it. Storage. And then we get the message. And we get the message ID. What is this? Okay, message metadata. And then we have the tangle storage message metadata, message ID. So we have both of these things, and then we will need to get the tip sets of the that represent the given color. So we would most probably need to have a function like tip sets message metadata inherited color. And that should return as, okay, let's implement that first. So we will need to have a getter that returns the tip sets that are covered by a given color, because we want to add the tip to all of the sets that are represented by that color. So tip manager, tip sets, color. And we have map color tip set. So tip set per color. And then we will say if the tip sets, the color that we're requesting doesn't exist, then we would create the tip set object. So the first time we retrieve it, it's gonna be created. New tip set. And then I guess that's everything. Then we also, of course, need to define a new tip set function. And the tip set will have some functionality. Okay, then if the color is undefined color, so if we see a message that has an undefined color, then that is compatible with all existing tip sets, because the undefined color represents the non-conflicting master reality, essentially. So here we can just return all the tip sets, and otherwise we just return tip set and we have color tip sets. Color. Does that make sense? I think so. So if the color that we requested doesn't exist, we initialize it. If we have undefined color, then this represents everything. And if we have a specific color, then we return the tip set of this color. In the real version, in the real implementation, you would need to determine which things to return by traversing the DAG, this branch DAG. So it would be a little bit more complex than this, but essentially it's the same. So as soon as you retrieve something, you would then just need to return all the children of the given color. So here in undefined, we give all the children, which are all the colors. And then since the color is only a one-level conflict and we don't have nested conflicts in this simulation so far, we can maybe extend it later on. Or just if the tests and everything work, and just use the final version of the ledger state that we coded. But for now, I think that should be fine. And so if we have the tip sets of the inherited color, then this is essentially the strong tips. So that means we will add this to the strong tips. So for color tip set is range t tip sets tip set dot add strong tip message, because this is the color of the message, and all the tips that are representing the perception that this thing is winning, it would be strong tips. And I guess then we also need to have make color. Oops. We need to remember that this was added to a strong tip. So now if we add the weak tips, that we don't add the same thing again. Added as strong tip, color equals true. So we added the message to the strong tip of this particular color. And then we do the same for the weak tips. No, you don't need to have more than 6 parents for 100% confirmation, I think. Who said that? I mean, the confirmation rate definitely increases, but it essentially just speeds things up. It shouldn't really be relevant for the percentage. So, and if it was not added as a strong tip, then we add it as a weak tip. And then we need to, of course, also have the add weak tip and the add strong tip function in here. So, and then we also need to have the tips function that we need to implement. So add strong tip, add weak tip, and we need to have the new tip set. Oh wait, but we also need to, if we create a new new tip set, we need to inherit all the tips that are currently in the master branch, or like in the undefined color. So that means we need to have something like this, and then tips to inherit, I guess, and then that would be a tip set. So as soon as we create a child branch, the child branch, of course, inherits the perception that its parent branch is correct. So it should also receive all the tips that were there. Okay, so maybe let's start implementing the tip set completely first. So the tip set will have strong tips, random map, and it will have weak tips. And then the tip set will be a tip set, and strong tips is random map dot new, and weak tips is random map dot new. And then if the parent, the tips to inherit is not equals nil, then we can iterate through the strong tips for each consumer function, blah blah blah. And then we say tip set dot strong tips dot set key value. And then we do the same thing for the weak tips. And then we return. And then we need to have, what did we call the function? Oops, now I pressed F1 and my Windows help opened. Add strong tip. And add weak tip. So add strong tip, right? Tip manager, no, tip set. Add strong tip, and there we had the message, I think. Right? if I'm not mistaken. And the add strong tips function, add message dot id message, and then we remove, if we have added a strong tip, then we remove all the strong parents that we have referenced from the strong tips, because now they have been successfully referenced by a new tip. And then we remove the weak parents from the weak tips. So as soon as a new tip arrives that that references something, we just remove it from the corresponding tip set. Weak tips, weak parent, or maybe we leave it like that. So I think that is fine. And then we have the tip set. Add weak tip. And that is also a message. And in the weak tips, we just add the message ID. And that's it, because the weak tip doesn't reference anything, so it doesn't remove any existing parents or something. And then maybe we need to have a function to return the strong tips from the tip set, so we can retrieve that from the outside. God, the tip selector is the most complex thing in this whole components. And so the strong tips is message IDs. Well, we're soon done, I hope. So if the strong tips dot size equals 0, so if we don't have any strong tips, then we return the genesis. Because then the tangle is empty. And then we return. And otherwise, if we have strong tips, we make message IDs. And then we just strong tip in range t dot strong tips dot random unique entries, and then the max amount, and we add them to strong tips dot add strong tip dot message ID. And now nothing works because I wrote something weird here. So then we essentially retrieve the random map is again a data structure that we have in Hive, which just allows you to request random entries from a map, but you can also do get and set and stuff like that. And for the weak tips, I think the code should essentially be the same. But if if the size is 0, then we will just return nothing. So weak tips, and here we just return. We don't have anything. We don't necessarily need weak tips. It's just something that is optional to pick up stuff. And then we have weak tip in weak tips, and then we have weak tips dot add weak tip message ID. So now we have defined the tip sets, and we have defined the analyze message function. Are we done with everything and can run the simulation? No, there's still an error message here. And the error message is... okay. Yeah, of course, we need to have a function that returns some tips for us. So that means that we can essentially return the tips from the tip ledger. But I think that should then be the last thing. And the tips, first we retrieve the tip set. I guess the tips should return the strong tips and the weak tips. And they should be message IDs. And the tip set is t.tipset. Tipsets t.tangle opinion manager opinion. So we retrieve the tipset that corresponds with our current opinion. And then we get strong tips equals tipset dot strong tips. And how many strong tips are we gonna use? Maybe we can introduce some constants here so we can play around with this. So tips count, let's try with 4. And then we want to have the weak tips. So we will always have to have at least one strong tip. So that means, I mean, I'm planning to now implement a strategy where you collect as many strong tips as you want, ideally. And if you don't have enough, then you fill up with weak tips. Or if you don't have enough weak tips, you fill up with strong tips. So if the amount of weak tips is 0, then we're done. Because currently, if we want to select 4 tips, then we have potentially received 4 here and 3 there. So that means we have 7 tips. But if the weak tips is 0, then we can just stop, because then we have only 4 strong tips and we're done. And then we need to fill up with weak tips if we have not enough strong tips. So how do we do this? That would then be the first case. So if the strong tips count, which is the length of the strong tips, is smaller than the number that we want to have. So maybe we should also have the number that we're aiming at having in strong tips, like the ratio or something. How do we best do this? Because we don't want to have too many weak tips, because the strong tips are the ones that we use to inherit our perception and where we efficiently make statements. So we want to allow there to be some weak tips, but we don't want to prefer picking the weak tips. Like if you attach somewhere that is bad, then you shouldn't be worried about not being picked up. But if somebody is lazy and always attaches just to some old stuff or something, then you should not necessarily expect to be picked up. So in theory, these having to pick up things should not happen too often. So maybe we can say we want to have a weak tips ratio of weak tips ratio of 0.25. So like 1 out of 4 tips would should be a weak tip. And now we can do calculation. Optimal strong tips count equals float tips count, float 64 times 1 minus weak tips ratio. Is that correct? Or did I do wrong math in my head? So that means if we have 4 times 0.75, that should be the optimal string. Yeah, so that would be 3. And then we have the optimal weak tips count is the same, but times weak tips ratio. So that's essentially our numbers that we want to use in the tip selection. And then we would say here, if we have less than the optimal strong tips count, then how much do we need to fill up? Then we have more space for weak tips. So then we can fill up with strong tips count. So that means if we have like 2 strong tips, the tips count should be 4, then we fill up with 2. And then if the fill up count is bigger than the length of the weak tips, oops, we don't have to parentheses here. So if we want to fill up more than we have available in the weak tips, then we can return, because then we're done. We cannot really need to do anything. Fill up count. And otherwise, we just throw away some of the weak tips. Oh, we already have a length method. So fill up count. So we just throw away some of the weak tips, and the remaining ones are staying. And then we kind of need to do it exactly the other way around as well. So I can just copy this. So if the weak tips count is the length of the weak tips is smaller than the optimal weak tips count, then we need to fill up the weak tips with the strong tips. So if we have too few weak tips, then we just take more strong ones. So fill up count is length than the strong tips, so this would also need to be returned, and then the strong tips trim fill up count. Maybe I can remove this comment here. And then if nothing of this happens, so we have enough weak tips for the optimal count and we have enough strong tips for the optimal count, then we just trim them to their optimal length, and then we're done. So, and now the big question is, does everything work? What does it say here? You should use... Okay, I can remove that. We don't need to have a length for the otherwise. It just says that I should have comments everywhere, which is of course usually a good idea, but I wanted to save time, so okay, let's see if the whole thing compiles at least. Okay, it compiles still. That is a big surprise. Usually I expect it to crash. Now the question is, we need to of course do something in the main network. Like we don't really execute anything. We have the we create the network and then we don't do anything with it. So we don't send messages or anything. So the question is, are the nodes also being started? Network. So we create the network, we connect the peers, but I think we don't start the peers yet. Okay, this is the configuration. So we create the network, we create new configuration, random network delay, create peers, but that's in the configuration. I am in the configuration section. So okay, so we only create the network. We don't launch or install the nodes yet. That's also why we don't really see any of these log messages or something. Okay, so then maybe we should implement a function to start all the nodes and connect the, like, start the handlers that process messages and stuff like that. So we will have network start, and I think we already have a start method for the peers, if I am not mistaken, and that will be peer.start. Yes, and then I guess we also need to have a shutdown method. Do we have a shutdown function for the peers? So we have one. What do we do there? We close the shutdown signal, and then the worker will stop here. Okay. So then now we can do test network.start. So now all the nodes should launch and their tangles should be initialized and stuff like that. And we can also say defer test network shutdown, and then we do time sleep 3 seconds. I mean, we need to also still write some code, like we're going to issue messages and we will need to make the big mana holders make statements regularly and stuff like that. But I think we should at least see more output here. Or don't we have any log messages in the tangle? We don't have any log messages in the tangle. Okay. So, but don't we have one here somewhere? No, in the node. Log debug, setting up multiverse. Is that happening somewhere? Here, okay, we have peer 90 setting up multiverse. You know what, I will just reduce the network size for now to like 10 nodes. So it's a bit easier to see what's going on. And it's shutting down the simulation after 3 seconds. Okay, so at least nothing crashes. So now we need to implement logic to send some messages. So we can actually send messages, or maybe we also should have a function in the network that will give us like some random peers or something. So we can retrieve some random peers if we want to issue conflicts or something, that we can then access these peers from there. So that's maybe the best thing to start with that. So we have a network, and then we do random peers, and the count is integer, and it will give us random peers, and it's going to be a list of peers. And then we say selected peers. Oops. Peers is set of new, and then for length random peers is smaller than, why do I always make parentheses? That's weird. Smaller than the count. Then we say if random index It's crypto.randomness.intNn length, not node count, length n dot peers. And then if the selected peers dot add random index. So we generate a random index that is just a number of our an index in our list of peers, so from 0 to the amount of peers that we have. And if we can add that to the set, so we haven't seen that before, then we're just gonna add it to our list of peers that we wanted to select. So that means, and then we return. So if, for example, our random number generator generates the number 5 2 times, then this will only be true the first time we add it, and the next time we add it, it will return false, so we will not add it again. So we exactly get the amount of random peers that we want to have. So let's see if we can, for example, test network dot random peers 1, and then we take the first one, and then we receive a network message. We can say multiverse dot blue. So now it should create a message and import a conflict. And of course, it says invalid a message, because we most probably have some error here. So let's see, we have the message factory, it gets the tip manager. The tip manager is most probably initialized, so that's not nil. The strong tips is the tip sets. Aha, okay. Okay, so here we request a tip set of a color that we haven't initialized yet. So in the same way as we have the tip sets function, create the tip set the first time you request it, we need to do the same thing for the, if we want to have just a single tip set. And then we can fix this, so then we can say if tip set, so then we say tip set equal exists tip sets taking opinion. Oh no, here we can do the color. So this retrieves a single tip set, and if it doesn't exist, then we create it in the same way as we do here. And then let me copy this here. So we have t.tipset, our opinion. If it doesn't exist, then we say tipset equals this, and the color equals tipset, and then we can return, and then it should work. So let's see if that is the case. Okay, now we get another error, invalid memory address or nil pointer dereference. What does it say here? Is something wrong with our walker? So how do we go through the thing? So we do handle network message, we do process message, we go into the store, it triggers that we have stored the message. Oh, wait, maybe. Because yesterday I remember that we, in Go Shimmer, we had a different functionality for this, and then I thought like, oh, that's stupid, we can simplify this, but maybe I was wrong, and we cannot simplify this because it goes in the other direction. Yes, that is actually correct. Okay, I know what is wrong. Let me fix this fast. Store, because the strong parents are pointing from a message to its parents, and the children are actually a reference in the other direction. So there, instead of storing the parents, we would need to store a reference from the parent to the message ID. So that means I need to actually store the reference in the complete other direction. Otherwise, it will make me walk into the nirvana. I don't know. Okay, so then we need to have the store child references function that we had yesterday already, which I deleted again. So it was late. Maybe it was better to stop yesterday. It would have just gotten worse. Message.strongparents, and then we will have the same thing for the weak children DB and the weak parents. And then the store child references will be a little utility function that we have somewhere here. Storage, store child references, and we receive the message ID. That was reference. We get the child reference DB, which is a map of message ID to message IDs. And then we have the parents, which is again the message IDs. And then what we do is we iterate through the parents. And we check if the entry for this parent exists already in the child reference DB. Parent. And if it does not exist, then we create it. Here, this is wrong. Parent, not parents. Equals new message IDs, and then we just add the child reference DB parent dot add message ID. So that means we don't just store the parents in this database, but we iterate through the parents and store that this parent was referenced by the current message ID. So it's exactly the other direction in the mapping. And I think that's why we now walked into the nirvana. So let's execute the thing again. Okay, now it doesn't crash anymore. I mean, we also don't really dump any information when we process a message or something, but we can maybe add a log message here. So or maybe we can actually write a function to monitor the network or something in the main file. So maybe we can just write a function monitor network state, and then we hand over the test network. And then we will create a function, monitor network state, and we can make it dump a state every like once a second or something, where we can then see the TPS and stuff like that. So we will most probably need to have some variables that we want to track. So we want to have a TPS counter, which would be a uint number 64. We would maybe have if we want to track consensus, we need to have the map of the color, and then how many nodes are following this color, so we can see how many of the nodes are having which opinion. We most probably need to have a mutex for that, because all of the nodes are running asynchronously. I didn't make the TPS counter mutex because we can use that with an atomic accessor. Then we need to have a message counter, maybe. Maybe TPS counter is already the message counter, right? So we have the TPS counter, the opinion mutex, and that's essentially it. So maybe we initialize the opinions here, and we say multiverse.undefined color equals node count. So initially, the network, we call it nodes count. Yeah, initially the network will obviously start with all nodes believing in the non-conflicting perception of the undefined color. Multiverse dot, do we have colors? We had blue, red, and green or something. Oops, I think. Oops. Blue, red, green. And then we need to now we need to iterate through all the peers and attach to the events and see peers. Do we have peers there? Ah, we don't have network.network. So then we need to attach to their opinion updater event. So we have the peer, and we need to get its node, and then why don't we have the tangle and everything? Ah, okay, because we need to typecast it to the multiverse node. Tangle dot opinion manager dot events dot opinion changed attach, and now we have a function, and that should be the old opinion, which would be do you guys still hear me? Because I just got a message that I lost the connection. Okay. Super weird. I hope my internet is not dying. Dude, then it would be like another evening. That would be really annoying. So, okay, and then we have the opinion mutex. So we need to lock. So it's thread safe, and then we have the opinion mutex dot unlock. Oops. And then we would increase the, no, we would decrease the number of nodes believing in the old opinion, and we would increase the number of nodes believing in the new opinion. So now we're tracking the consensus in the network. And then we maybe also want to have a periodic message which tells us how the network status is currently, like how many nodes are believing in what and stuff like that. So then we can just use the logger, and we do the info format, and we can say network status TPS, and then we say consensus %d undefined, %d blue, %d red, %d green, And then we have the TPS, how did we call it? TPS counter. But I think we need to use the atomic load int or something. Oh, why is this not correct, by the way? Ah, because I forgot the new closure thingy. So here we would say atomic dot load uint64 and TPS counter. Then we have opinions multiverse dot undefined color. Maybe I can have this a little bit indented here so it's a bit easier to read. We have undefined, we have blue, we have red, we have green. And now let's see. Let's maybe not send a color yet, but we just send or we send the undefined color. Let's see if this works for now. The TPS is not being tracked yet, so we should, in our output, we should only see, okay, 10 undefined, 10 undefined, 10 undefined, and we dump that every second. So maybe I should write this little utility function to send a message also to a given node, so we can then track the TPS counters. So just to see if the message, if the nodes actually do something. Then network here optional color is multiverse.color. Make dot add uint64 and TPS counter 1, and then if the length of the optional color is bigger than 1, then we issue multiverse.node.issue payload. Oh, why does it not work? Issue payload, do we have that? Oh no, we don't have an issue payload function in the node. Okay, we only have the setup and the handle network message. Maybe it would make sense to introduce a issue payload function or something, so we can directly send the payload to the message, to the thing. Okay, I will implement that function. It's really simple, right? We just have n node issue payload is a color, and then we just inject that into our socket, and then it will be handled by the network message, and if it is a color, it will be processed by the message. It will create a message and issue this. So then it should have an issue payload function now, and then we can optional color 0, and otherwise we have to do the same thing but with the undefined color. So multiverse dot undefined color. So now we should see one TPS, I guess. Well, send messages out first. Where is the... Okay, so we have send message to this peer. Let's see if we see there's like one TPS somewhere. Okay, we have one TPS, but we only send one message once. Why does it show us one TPS forever? I think it should show one TPS and then 0 TPS, no? So there seems to be something wrong with the code. So yeah, after we show the network status, I think we need to reset the counter again. Okay, let's do that. Okay, now it starts with 1. Okay, so now for the network to reach consensus, of course, we need to generate some kind of honest activity. Like the network needs to issue messages regularly to for the network to function. So, or for the nodes to reach consensus, it's not enough to just send one message and then be done with it. So we will need to implement a function that will generate some honest activity. And the big problem that we had with the original version of IOTA was that the network was secured by proof of work, of course, right? And proof of work is like the proof of work was not very high, so the security of the network was also not very high. And to make the network more secure, you would essentially have had to create a lot of proof of work to secure the network, but who would do that for free? I mean, you don't get any fees or anything. Who would mine transactions with a high proof of work in a systems where you cannot earn anything? Now, since we have a reputation-based system, this is a different story, because the high mana nodes, they can easily just send out a short message with their signature and 2 tips that they reference. What is with opinions plus? Oh, yes. You are right. I have not seen that. So in the new network, we will just make it part of the protocols that the large mana holders will every now and then just send a short message and inform the network about their opinion, and therefore secure the network with their honest messages. And of course, at some point in the future, if there's enough honest activity in the network, you might not even need that. But for the beginning, I would say, like for the times where the network is new and you only have like 10 TPS or something, it's definitely something you need to make the network secure. So after we have the monitor network, we will maybe write a secure network function. We can also hand in the test network, and then we will maybe have some time-based parameter which says how often these security messages should be sent. So we maybe want to have some confirmation time of around 500 milliseconds. That would be nice, I guess. So then we can define the pace here. And I've actually thought about this, how we would secure this thing before, so I think I have at least an idea how I would code that. Let's see if it works and to how many TPS that would actually translate, because I've never really tried it or did the math. But the idea is essentially that the highest mana node would send out a message or like a statement every 500 milliseconds, for example. And the second highest mana node would then, if he, for example, has half of the mana of the first one, would send out a statement every second. And then the third highest mana node, who maybe has like a fifth of the mana, would send it out every 2.5 seconds. So inversely like scaling. So that means that if you have 10 times less mana than the highest mana node, then you would send it send your message 10 times less often. And a node who has really very little mana, like a sensor or something, maybe doesn't even need to send his opinion at all at a given time, because if nobody cares about him, then why would we make him work, right? So we have the secure network, and the first thing that we would need to do for this formula would be a float 64, and then we need to have the weight distribution. Oh, we don't store the weight distribution in the network. So I would need to retrieve it from a node. That's a bit annoying. Maybe we should actually store that here. So then we have the weight distribution, and that is a consensus weight distribution. And where do we generate the new consensus weight distribution? Here. And then we can say network dot weight distribution equals this. And then we can also say this here and this here. So then I can see the weight distribution in the network also from my main test file. Otherwise it would be a bit annoying to get the value. And then we want to have the largest weight. That's also why we implemented that. I mentioned that already at the beginning, that we will most probably need that. So then we go through the peers, test network.peers, and then we determine the weight of the peer, which is then typecasted to float 64, so we can calculate it with our pace factor thingy. And then we have the weight of the peer ID. And then maybe we want to have a cutoff condition, so somebody who has 1000 times less weight than the largest mana holder, he doesn't need to do anything. So if the largest mana holder has like 10,000 weight and you don't even have 10 weight, then maybe your voice in the network doesn't really matter that much anymore. And then we want to have, but maybe it makes sense to actually count how many relevant validators that would yield. Like how many relevant validators do we have if we do these rules? That would maybe be a good number. So the relevant validators is an integer, and then we just count how many times relevant validators plus, I guess. So we increase that, and then we start security worker here. And then how often do we need to do this? It's going to be a time duration. And it will be the largest weight divided by the weight of the peer. So if the largest weight is 4 and the weight of the peer is 2, then this will be 2 times. Then we multiply that with the float 64 of the pace divided by the time in milliseconds, and then we multiply that by time milliseconds. Does that make sense, or is it stupid to divide by milliseconds and then multiply by milliseconds again? But I'm not sure if I can do this calculation, because otherwise I will have a type, but like a type conflict, I guess. I guess it has to be like that. But it's kind of weird, like you divide by milliseconds and you multiply by milliseconds again. But let's see if it will work like that. And then we have start security worker, and then we will have the peer network peer. But this means that essentially after 500 milliseconds you will already have, most of the times you will already have the confirmation of the largest mana holder. So he needs to send out 2 transactions per second, but it's not really that much. Especially considering that in FPC he will be queried by every node in the network eventually. So it's much easier for him to just send 2 messages than to answer potentially thousands of people. And so our security worker is essentially just a function that continues to send messages through the peer. So now we have the secure network function, and now let's see, maybe let's increase this to like 10 seconds or something. Now let's see if this, oh, maybe we also want to see in the network state how many validators we have and how many nodes we have. So maybe we can increase this information thingy here. So we can say that many nodes and that many validators. And then we say the nodes count. And then we say the relevant validator count. And relevant validators. So now let's see. So we're very close to run consensus tests now. Okay, so we will have a message overhead of like 4 TPS. Oh, okay, but we have also a really small network. We have like 10 nodes, right? Let's do it with 1000. Because then we can think about what would be a good parameter for this number. I think as long as the TPS, the message overhead for the securing the network is not larger than like 21 TPS or something, then it should be totally fine, because the 21 is around the numbers that we query in FPC as well. Okay, so that doesn't look too bad. So we have like 10 TPS message overhead in the normal weight distribution. That actually looks really good. So let's see if we have a zip distribution. Let's see how it looks like with 10,000 TPS. But as I said, like as soon as you have enough honest activity in the network, you can also remove this securing the network messages kind of thingy. So we have 2,133 validators. That is not even that bad. That are relevant for the consensus, kind of. And depending on how much total mana you have, it kind of fluctuates a bit, but I guess you will have around 10, 11, 13 TPS, something like that, to secure the network. So now maybe let's issue a conflict. So we can get random peers. And we will get 3 of them. Attackers, we call them. I know. And then we say send message. Attackers. Then the first attacker will issue multiverse.red. And the second attacker will issue multiverse.blue. And then the last attacker will issue multiverse.green. We have green, yeah? And then maybe let's run the network for 30 seconds, because I have no idea how long it takes to actually reach consensus. And now let's see if something happens. I hope there's no other bug, hidden bug or something in the system that we have forgotten. Okay, so we see it works. The network reaches consensus on red, essentially in 1 second. So no panic. Okay, so that's actually really, really fast. And even in the 10,000 node network, you see already 7,648 nodes have even tipped before we see the first status message of the network. So that is really, really fast. I will just rerun it again just to see how it performs. I also have to note that, of course, it's again red that wins. Let's see if always red wins. This time blue wins. But yeah, essentially like within like a second or something you will reach consensus. But I'm also not really sure if let's go to like 1000 nodes, for example, and the mean degree is 4. Oh, that's kind of fine, I guess. So yeah, okay, here you essentially, if you have less nodes, because I only have 4 CPUs, right, and it's like simulating all the nodes at the same time, so the time that you see here is not really that representative, because it essentially, with 1000 nodes, it's essentially processing 60,000 TPS if we have 6 TPS here, right? Because it needs to do the 6 TPS for all the 10,000 nodes. So I think it's pretty fast, and it looks really reliable and good. And to be honest, I don't know. I mean, I think it's very unlikely that an attacker can keep such a system in balance, because it just tips way too fast. How would you time your attack if this whole thing reaches consensus in a second? And after 500 milliseconds, you already have a statement by the largest mana holders that confirms the winning branch, right? So to tip it back, you would need to have more mana than the largest mana holder, which is kind of not really possible. We can also delay the attack. So we can do time.sleep. Like, I don't know, so we have the network undecided for a few seconds, and then it starts to tip. So now we're undecided, now it should tip, and it's immediately tipped, like within a second. It's essentially sub-second consensus, more or less. And I want to see how much, like what happens if we let red arrive there, like, I don't know, maybe 15 milliseconds earlier. Will it always win? Like how much time difference, or let's do 20 milliseconds or something. How much time difference does a transaction need for the network to always take the first one? That would be something that I'm really interested in. Okay, so red won, and red is the first one in our first test. So now let's do this. I mean, it kind of makes sense, right? All the nodes follow exactly the same rules as soon as they have reached, as they've seen the same messages, they will essentially have the same perception. So, and since the network delay is something in the realm of like 650, 700 milliseconds or something, you would most probably assume that you would have consensus in like 750 milliseconds. And if you then make the largest mana holder send statements every 500 milliseconds, then you essentially have finality, more or less. Depending, I mean, if you really want to wait for all the consensus mana to commit, then, or more than 50%, maybe it takes like 2 or 3 seconds. But if you're, for example, selling a coffee, then maybe you're fine if the winning option is already ahead by 20%, because everything else will just follow. Okay, you guys want to see the thing more often, so let's do 100 milliseconds. I can also commit this. We could also, for example, build a web UI for it, so you can see it, and maybe, I don't know, add a... Oh, now my sound fell down. Do you guys even hear me still? Wait, I need to climb behind the table. So, okay, I'm back. So wait a second. Now we have the every 100 millisecond statement. Of course, the TPS numbers will not be correct now anymore. But now you see how it tips. So you have 992 undefined, and then it looks like it's tipping towards blue. Some people believe in green, then they lose their weight again. They catch up. So yeah, I think it's a pretty big success. So it does work. It doesn't create a lot of message overhead to secure the network. If we assume a zip distribution, it's fast, and yeah, I'm really looking forward to research this a little bit more and like have formal models also in math maybe to describe what's going on. But the fact that it's tipping so fast is definitely encouraging, because that removes the attack vectors that a potential attacker would have by a lot. If it would take like 3 or 4 seconds to tip, then maybe you could time attacks and like switch back and forth and stuff, but how would you switch in like 500 milliseconds? I guess we can expect it to be on a testnet relatively soon. I mean, now we have the code more or less in like a template for it, kind of. As soon as we're done with the FPC prototype, I will definitely port this over to the GoShimmer code, and then we can test it on a testnet. But FPC still has the highest priority. I mean, it's the way we're gonna go with Codicide. So, I mean, unless this, yeah. So I think as soon as I have a little bit of time. But of course, now it's also going to be interesting to implement some additional attack strategies, like so we can add a few more nodes here to the network and say like they are using like a certain attack strategy, for example, to see how it behaves, or we can also simulate how the network, if the network still tips, if the nodes have different perceptions of the weight, for example, which is something that I think should still work. I'm not entirely sure if that is the case and how good it is the case, but I think it should work even if nodes have slightly different perceptions of the weights. And I think it should even work if they have pretty big differences of the weights. The colors, there was a question, what do blue, red, green represent? Well, to detect conflicts and stuff like that, you need a pretty complex data structure, which we call the parallel reality-based ledger state. And implementing that in a live session would have just taken way too much time. So instead of making the nodes vote on transactions or like on conflicts, I made them vote on colors. So it's a little bit of a simplification, because for the voting mechanism, it doesn't really matter what they vote on. And then I didn't have to implement all the transaction logic and the balance checks and like everything that comes with it. But ultimately, if you have a consensus mechanism, then you want to reach consensus on some value. That can be anything. Can, for example, be if the block is valid, yes or no, or if you like the transaction, yes or no. And most consensus mechanisms are binary consensus mechanisms, so you can only decide between 1 and 0, and this one is a colored voting mechanism where you can decide between an arbitrary large amount of options. So if I would give this with this mechanism 1 million options, then it should still decide for exactly one color in essentially the same amount of time. It's instant consensus, essentially. That's true. Yeah, I'm pretty happy. I will push this. I will commit this. Maybe I will also add some comments in the coming days if we have time. Added first consensus tests. And then I guess people can play around with it. We can use it for simulations, and yeah, maybe somebody feels like writing a web UI or something. I think that would be it. If anybody has questions, maybe we can meet in Tanglemouth and talk a little bit about these things. Good night, guys.